Hello everybody, I'm Professor Hammond. I am going to be your instructor for Math 465 this term. So as you may know, I'm not in the class physically. The reason for that is that I am right now expecting a new baby. My wife is going to be delivering by C-section on Tuesday, which is the day before this class is due to be given. So that's why I'm not here physically. I'm going to be recording video lectures for the first two lectures, and then I will see you all in person on the third week of the term. So I'm just going to proceed as if you were all here. It's a little bit strange for me. In order to help me deal with this, it's kind of strange to be lecturing to no audience, so I'm going to introduce our model student. This is Charlie the squirrel. Say hello. Alright, so I'm going to be delivering this lecture to Charlie. Charlie's going to be hanging out over here and maybe asking me some questions during the time of the lecture. I know it's a little silly, but I feel like I'm going to do a better job if I have somebody to speak to. Alright, so let me introduce myself personally. So I originally from the Northwest. I grew up in Tacoma. I went to college at Caltech. And afterwards, I joined the Peace Corps for 2 years, where I was teaching math in rural school in Malawi, in East Africa. After that, I moved to New York City to do my graduate work, got my PhD there, and then did a series of research postdocs, first in Switzerland and then in Eugene at the University of Oregon. So my research interests are in signal processing, and sort of broadly defined. I've done a lot of work with EEG analysis more recently. So this is signal processing and signal estimation of brainwave signals. But anyway, be that as it may, I'm here. And I'm relatively recent faculty here at OIT. So I just began this past fall. So this is just my second term. So this seems a little bit impersonal to not have an audience here, but I'll just try to break that down by personally saying hello to all these students. So I have not met you yet, but Logan, Jesse, Joel, Carissa, Christopher, Robert, Alan, Smahani, and Colin, I'm really looking forward to meeting you in 2 weeks from now. Anyway, let's begin. So the book somebody should have passed out a syllabus. This is pretty standard. What do I want to say about this? The thing that may be a little different is this class is going to have a significant in-class contribution. So we're going to be doing work in class in groups, and this will be counting for your grade. So if you miss the class, you're going to miss the points for the in-class assignment, and that's an additional incentive to come to class. Grading is going to be pretty standard. The book is this one by Richard Larson. And in addition to this book, I'm going to be posting some supplemental material prepared by Greg Waterman, who's a math professor at OIT, but down in Klamath Falls, who's written a pretty concise and nice complement to this material. So that will be posted on Blackboard as well. Definitely during this first 2 weeks, as I'm not physically here, feel very free to contact me by email. Especially since I'm not going to have office hours and you are going to have a homework assignment from the material that we're covering today. Okay, so why do we care about the course material in this class? So the title of this class is Mathematical Statistics. This is perhaps a little bit misleading. The material that we're really going to cover in this class is probability. So probability is a branch of mathematics that deals with randomness. So at its core, probability theory is a set of tools for describing and modeling doing calculations to figure out the likelihood of random events occurring. So why do we care about something like that? Well, you may care about it because you need the credit, but a better reason to say is, well, you're going to go on and do great things as scientists and engineers, and you have to deal with the world as it is. And the world is not deterministic. The world is not cut and dried. There are many things in the world that occur randomly. So you don't know exactly what's going to happen, but you have some degree of random behavior. So what are some examples? Here's a very easy to understand example of a random process that we're going to be talking about a lot. So this is a standard 6-sided die. You can roll it. Charlie will verify that I'm not cheating. And what comes up? A number comes up. All right, so what came up? 2. So I can do this repeatedly, and every time that I roll the die, potentially a different number can come up. And I don't know in advance what's going to come up, and it's certainly random what's going to occur. Okay, so this is sort of maybe a toy example, but it's a very concrete, specific example of a random process that we can build into, that we can describe with probability. So, make it a little bit more complicated. We could have not 1 but 2 dice. Oh, sorry. So, okay, in that case, we had these 2 come up, and then I could roll them again, and something else comes up. Okay, so, that's one example of something that's random. Another example, I have a deck of cards, shuffle them, and pull up a card. So, Jack of Hearts came up. Well, something else could have come up. I can shuffle it again, and then, boom, different card comes up. So that is another example of something that's clearly random. There are many other types of examples in the real world. So, for instance, I could ask the question, well, is it going to rain tomorrow? Well, we live in Oregon, so that may cut down a little bit on the randomness. But basically, either it could rain tomorrow or not, and there's some likelihood of that happening, and that's something that we could think of as describing probabilistically. I could ask other questions that are not. So all of the examples that came before are so-called discrete, because there's only a finite number of outcomes that can occur. So when I rolled the die, 1 through 6 would come up. When I pulled out a card, there's 52 cards in the deck, so one of them comes up. If I'm asking you if it's going to rain or not, I'd ask that as a binary question, so the answer is either yes or no. But I can ask other questions that are random events that are not giving just a discrete set of outcomes, but can give some real number that can have a continuous variable. So if I'm talking about the weather, I could ask tomorrow, what will the high and low temperatures be? So these are going to be 2, real continuous measurements that could come up. And I may want to ask questions about how likely is it for the temperature to be between this range and this range, and so on. Just other examples. How likely am I to get in a car accident on my drive home from work today? Okay, so that's a binary thing, because either I get in an accident or I don't. If I ask, how long is it going to take me to get home from work today? Depending on traffic conditions, there may be some randomness involved in that. Who will win the big game? So outcomes of sports. There's lots of. I'm not a really big sports guy, but there are lots of examples of random behavior that come up when you're talking about sporting events. So in particular, baseball, people go crazy about thinking about all the different random events that can occur or that you can measure from a baseball game. Okay, so those are all sort of one class of random things. Another very important place where randomness comes up is when we're thinking about data. So what I mean by this is the following. So whenever you're measuring anything, there's going to be some inherent variability in either in the population of what you're measuring or in the process of making that measurement. So here's a kind of example that I'll pick. So if I describe a random event as to say, go out onto the streets of Portland, find a random person, and then measure their height. So that's a process where you can think of potentially repeating that many times, and each time you're not going to get exactly the same answer because you're not necessarily going to pick exactly the same person, and even if you did, you may have some error in measurement. So that's one example of randomness involved with measurement. Another example could be the following. So if I say, hold on a second. Sorry, I'm just going to change the settings here so that this doesn't display. Okay. Sorry about that. It was just turning off my display, which is kind of confusing to me. So another example of this could be, I say, how long is Charlie? So we're going to take, my question to you is to take Charlie and measure his length from nose to tail. Okay, so with a measuring stick. So I ask one person to do this, and he comes out with a measuring stick. Blah blah blah. That's like 19 and a half inches. And somebody else may come along with a different measuring stick, measure exactly the same animal, but because of small variabilities in either the construction of the measuring stick or how they're using the apparatus or whatever, may say, he's like 19 and 3/4 inches. So you're doing a repeated measurement. The process is measure this object or this stuffed animal, and you get different answers different times. So there's some variability. And here the variability is not coming from variability in the population, but is just coming from error in your measuring device. So that's another place where randomness can come in when you're talking about measurement. All right. Okay, so I noticed there were a number of software engineers and electrical engineers in the group. So other things you can think of is, okay, you build a web server, put it up. How many hits does your web server get in a given 1 hour period? So that's a random process where knowledge about that random process may be important for the design of the architecture supporting that website. Or if you're thinking about electricity usage among a small town of 5,000 people, how much electricity are they using at any given moment? Well, it's not constant and it's not deterministic because at each individual time, different people may go and turn on the lights, and turn off the lights and whatnot, and start cooking dinner and stop cooking dinner. So there's a lot of randomness in the electricity usage. And I guess I'll have to admit I'm not a practicing electrical engineer, but perhaps you would need to describe that randomness in order to build a system that can be robust to that type of variability in the demand. So these are just motivating questions. All right. So why should each of you care as a hopefully budding scientist or engineer about any of these things? Well, the real bread and butter of experimental science is dealing with data, and you need a solid background in probability and statistics in order to do proper inference with noisy data. So I'm going to kind of put some toy data up on the board. So suppose that you were inspecting light bulbs coming from different light bulb factories. So you work for the light bulb company, and there's factory A, produces light bulbs, and you test them and see how long it takes them to burn out. So this is, you test 4 light bulbs from this factory. And this is how many hours they take to burn out. So 1,010, 1,160, 1,330, 1,463 hours before they burn out. And then you go over to factory B, which is producing the same product, and you test light bulbs from them. And these are the numbers that come back from your test. So you have to answer some questions. So first question may be, is there something different happening at factory A or factory B? So you may ask questions about this data. Like, from this data, can we infer that factory A has higher quality or has longer lasting light bulbs than factory B? Now, the simple thing to do would just be take the average and say, well, if the average here is lower than the average here, then maybe these are on average have a shorter life than light bulbs from factory A. So you better hire a management consultant, fire the management in factory B, make some heads roll. But there's a lot of randomness in this data. So is it also a possibility that actually the process that produces light bulbs in factory A and factory B are exactly the same, and it's just factory B got a little bit unlucky here to have these numbers be lower, and in fact if you had more data, it would show that there was no substantive difference between the underlying distribution of lifetimes for the light bulbs produced in the two different factories. So this is really a statistical question. In order to have the tools to answer this kind of question, you need to understand the tools of computing underlying probabilities in order to be able to develop mechanisms for answering this kind of question. I will just tell you, for this data, I actually sampled these randomly from the same distribution. So even though it looks like these maybe are smaller than these, there's not enough data to make that claim, to support that claim in a robust way. So the tools for being able to explore that kind of question rely upon the types of probability that we're going to be learning in this class. Okay, so another area, perhaps as motivation, is so one thing you can do with probability is just kind of model and compute the likelihoods of different things happening. So, for instance, if I go back to the die that we had, I could ask you, what's the probability that if I roll a single-sided die, the number 3 comes up? And if you think about it, there are 6 possible outcomes, and each one of them is equally likely, and so the probability of getting a 3 is going to be 1 out of 6. So that's a very simple example of just using probability to compute a probability of an event occurring. So you can ask more complicated questions like that, like, I don't know, if I roll 20 die, what's the likelihood of rolling between a 60 and a 70 if I add all the numbers up. So we will develop later, when we talk about combinatorial probability, we'll talk about the tools for developing how to compute those sorts of questions. But another kind of question that we can ask from probability theory is not just what's the likelihood of doing something, but what you can use. There's a way of developing probability theory in order to guide decision making. So, for instance, I don't know if many of you have played the game of blackjack. It's a simple card game where you play against the dealer. I'll deal a card for the dealer and a card for you. Okay, so in this case, this is kind of awkward. I have to hold these up. But suppose you're playing against the dealer, and this is what the dealer shows, and this is your hand. Okay, so the objective here is to get as closest to the number 21 as you can. If you go over 21, you lose. And if you get better than the dealer at the end, then you win. So you can use probability theory to answer questions like, okay, if the dealer is showing queen, which is 10 points, and I have 16, should I hit on it or not? So that's a different kind of question than asking, if I'm showing 16 and I ask for another card, what's the probability of me going bust? So that question is just asking a simple probability. If I ask the question, what's my optimal strategy given that the dealer is showing 10? That is a so-called decision theory question. So all this is just motivation, but the probability theory can also be used to answer questions like that.